We enter now the nonlinear phase of global warming, and this means we observe an intensification of the coupling between the systems, which forces other systems into stronger states and hitting into systems which lost their resilience and are more prone to large changes. This means this abruptness of changes will now fast intensify, and the next temperature jump will us bring into highly critical waters, I think.
Welcome. I'm Dale Walkonen, and this is Facing Future. The planet's temperature is rising. Nowhere is this more evident than in our oceans, which have absorbed 90% of the heat that our industrial civilization produces. Our water world is in peril as sea surface temperatures rise sharply and glaciers dissolve at both poles. Disbalancing ocean salinity and shifting polar vortices, leading to weird, new, and unpredictable weather patterns. With me today to discuss the accelerating climate crisis are German Earth System analyst Jan Omsonset and climate scientist Paul Beckwith. Welcome to you both. Jan, it's good to have you with us today.
Thank you, also.
You've said that we need to look at the Earth system as a whole to really understand what's happening, what you call a wave train of events. Can you tell us about that?
Mm-hmm. I mean, the general understanding of Earth is that it's a slow changing system. The problem with Earth is highly nonlinear system, and abrupt changes in the subsystems of Earth are common, are not the exception. And the thing is, the subsystems of Earth, many of them are highly dynamic and can change very fast. Take, for example, the atmosphere. It's a highly dynamic system with many with abrupt changes that can build up and dissipate again. Or take the ocean surface. Surface ocean warming. It's just the upper mixed layer. This means just the upper 100 meters, 10 meters, 20 meters during summer. Or winter deeper, some 100 meters. But the surface oceans can change fast. Or take the Greenland ice sheet. We think that Greenland ice sheet changes slow. But if you look at the subsystems the Greenland ice sheet consists of, you have, for example, albedo. The albedo of the ice sheet can change very fast. You just need large wildfires in the Arctic Circle. You need the circulation patterns distributing the soot on the ice shield. Then you have algae growth that speeds up, darken also the surface. So the albedo, for example, can also change very fast. Then you have currents in the oceans. Over here we have lots of currents that are now discussed that they will change, speed up, slow down, or break down. So also in the current system of the oceans, also they can change fast. Then we observe now how whole biomes on the terrestrial land masses, Canadian forests, for example, the fires in 23 suddenly may boom, and exceptional peaks suddenly happening. Or like a soot concentration in the stratosphere. We observe now how wildfires get larger and larger, and because it gets drier and drier, though they can expand much more faster, create their own weather system, and suddenly pump high amounts of soot into the stratosphere. So also the black carbon concentration in the stratosphere can change fast if you get a large number of big fires in a single year. So all these things combined mean maybe we underestimate how fast Earth can change. And this means in terms of extreme weather events, that's one part. Our main problem now, they go up nonlinear, floods, heat waves, also large wildfires, not wildfires in area extent, but the large wildfires, they increase at high speed. And also marine heat waves you have. So also temperature maybe can also increase faster than we thought possible. Like, for example, now the recent acceleration, it was not foreseen. Now we have an acceleration, things like this. And this is the reason I think you have to see Earth as a whole. You have to look at all the subsystems, how they change, how they behave, how they are projected to behave, how they are interconnected, and how they can mutual amplify and force each other in new system states. Yeah. That's the reason I think you have to see it as a whole.
There's a lot
That was a tour de force. You can speak more slowly. I know the climate crisis is accelerating, but we can still, because the audience needs to absorb what you're saying. So I'd appreciate that.
You can watch the video on half speed or
Yeah,
something
this is,
on
yeah, I think
YouTube,
you
right?
can stop the video, you can watch it again.
People often
And
tell me they watch some of my videos on 1.5 speed, right? So
They
I say,
speed
well,
it up.
yes, yes. So Yan is a prolific poster on Facebook and other social media, and I'm surprised. Do you sleep at all, Yan? Because I see
I
stuff
try not,
constantly.
I try not to work at night, but I
Try
love
not
it.
to work at night.
I,
So
I,
let's talk
Mhm.
about, okay, I mean, the oceans and the atmosphere are key, and I think it's hard to capture all these processes that you're describing in computer models. I mean, the models just seem to be out to lunch. People often do statistical studies, and that kind of averages things out, and it misses a lot of the key things. So let's start with the atmosphere. People are well aware of the jet streams, right? How they guide weather patterns and stuff. But the way that air in the atmosphere circulates, a lot of it starts at the equator, right? Equator is warm, poles are cold. You have to get heat transfer from the equator to the poles. We have a system called the Hadley cell, where the hot
Mhm.
air is rising at the tropics, it spreads out, it goes poleward to about 30 degrees north latitude, 30 degrees south, and then descends down. You get the Hadley cell, and then there's gears. You get the Ferrel cell further north in the mid latitudes, and then you get the polar cell. So you had quite a few posts on how the Hadley cell is strengthening and the
Mhm.
implications of that. Do you want to go into that a little bit?
Yeah, I mean, the main change we observe now that came as a surprise, the surface of the planet and the atmosphere, ocean surface, land masses surface, the coupling intensifies. This means one affects the other more, and then it feeds back on the surface or back again on the atmosphere. And this means what we observe now an intensification between surface processes and atmosphere processes. And one of these intensifications is higher sea surface temperatures across the tropics, mostly the Indo-Western Pacific warm pool, the largest warm water mass of Earth, about 28 degrees is the definition. And this warm pool expanded by 100%, doubled the size now. And you get a larger amount of convection. The convection rises and it goes poleward. And these air streams going poleward, they disrupt the jet streams and make it wavy and stuff like this. And downstream, you get knock-on waves and stuff like this. But most important is it's hot upper air. So in the tropics, hot upper air is produced by large amounts of precipitation, and these hot upper air comes down the high pressure belts. And we have now these insane heat waves in the Mid East, North Africa, for example, also like in Southeast Asia or South Asia. And often these heat waves are intensified by hot upper air that sinks down over them and which is produced by a large amount of precipitation. So this means in Hadley cell of which upper circulation is intensifying, goes more poleward. This means more hot upper air comes down over the heat waves and reinforces them. And this is a large problem. Then you get more stuck weather patterns, more blocking patterns, because mid-latitude circulation starts to become more wavy, like you blocking and jet streams. Like you had also this topic.
Right, right. So then the Hadley cell then connects like a gear to the
Mhm.
Ferrel cell, which is the mid-latitude circulation cell. These cells, of course, very importantly, create low pressure areas and high pressure areas on the surface of the Earth. So the Ferrel cell is also strengthening and expanding. Okay,
In a
so
way.
so therefore the polar cell has to be shrinking, getting smaller in size. Is that correct? Like, and
Difficult. Actually,
yeah. Mhm. Well, how can the Hadley and Farrow both get larger and
for
stronger and
for
then not, how does the polar cell change then? It has to get smaller. It can't get larger. The Earth is only so big.
I had like now a recent study also on the Hadley cell, and the Hadley cell gets squeezed. The intertropical convergence zone moves north, and those thereby it reduces the latitudinal extent of the Hadley cell in the northern hemisphere. So
Right, right.
it seems like the Hadley cell gets in the northern hemisphere and moves northward, but also gets smaller because the intertropical convergence zone goes also north.
And the intertropical convergence zone, this is a band of tropical rainfall, usually
Mhm.
based close to the equator. And this is what has impinged on the Indian monsoon, which has pushed up against the Himalayas. And it's actually been seen on satellite images to actually
Ah,
cross the Himalayan divide and provide lots of rainfall to very dry areas in Tibet. I think the key point is all this stuff is very much connected, and we need more people to think of systems, right? Like most scientists, they specialize. Everybody wants to focus on one specific area and become an expert, but we need to understand how all the pieces of the puzzle go together. So, I mean, this is what I love about your post because we think exactly the same on that. It's a
mhm.
system that's key. So we have a problem. We focused on the Arctic, but Antarctic, meanwhile, has come and changed completely in the last decade,
Yeah, full
completely and
surprise.
utterly
Full
with
damn.
sea ice. So let's talk about Antarctica a bit and also the Arctic.
In a way, we could say the future of humanity decides around the South Pole, more or less. The Arctic
Yes.
is the main climate regulator of the planet, including the Southern Ocean and the Southern Hemisphere Ocean. Because it's like to heat up a water planet is a very stupid idea, actually. The oceans accumulate huge amounts of energy. They're a heat storage system. And most of this energy accumulation happens on the Southern Hemisphere because there are the oceans. There we have the area extent. And so we looked always at the northern hemisphere more, and at the southern we did not really we made research, but much less than on the northern hemisphere. And now we are fully surprised on how fast the Arctic is now changing. There's now a
Arctic or Antarctic?
Antarctic.
Antarctic. Yeah, you're saying you mean we're talking about yeah, Antarctic. Yes.
This high pressure system, you have now a high pressure system forming in the interior of the Arctic, which sucks in upper hot air in the interior of the Antarctic. And this is caused by this warming band in the southern Indian Ocean and likely maybe also the southern Atlantic Ocean. We have a warming band where lots of low pressure systems are forming. And these low pressure systems induce a teleconnection which supports the formation of this high pressure system in the middle of the ice shield, sucking in warm air. It's not so warm in terms of warm air, but for the Antarctic, it's warm. And we did not expect that. It was
No.
full new surprise now.
So of course, I mean, marine heat waves around Antarctica. I mean, that can't be that can't be good. And the models didn't capture it, as you say. Like
Yeah.
90% of humanity lives in the northern hemisphere. It's like less than 10% in the southern. It's hard to do research down in Antarctica. It's very isolated. We thought it wasn't going to change, and it's basically gone off a cliff in the last 10 years. The sea ice has collapsed. We're likely to have a blue ocean event, less than 1 million square kilometers of ice left. We're
In the
losing
Antarctic, we're
in
going to have a blue ocean
Antarctic.
event?
Yeah, that we're going to have an Antarctic blue ocean event far before any Arctic blue ocean event. But very worrying is I mean the sea ice provides a buttress to on land ice, slows down the glaciers on Antarctica. The problem is the warm water underneath is undercutting the ice and it's melting the Antarctic ice from below, especially on the West Antarctic ice sheet. And the system broke, 10 years ago. The changes in Antarctica are far greater than the changes in the Arctic right now.
And so
And
sudden, yeah. Just,
yeah, they're so
yeah.
sudden. And when you lose sea ice in the Arctic, it's at very high latitudes. Like it's at the North Pole, 90 degrees north. It might extend down, where does the land start in the Arctic? It's at lower latitude. What is the land mass is mostly what
75, 70 degrees, something like this. Like,
yeah, it's like 20 or 30 degrees latitude south of the pole. But Antarctica is totally opposite. Of course, we've got the landmass sitting at the pole. The sea ice is all around the edge, of course, of Antarctica, which is about 30, 40 degrees latitude.
much more
So it
north.
gets way, so if you lose ice around Antarctica, it's much more, has way more impact than losing the same amount of ice in the Arctic Ocean because it's exposed to far more sunlight, it's much lower latitudes, and people forget that. So this is changing the entire circulation system. And as Yan said, the Southern Ocean heat waves, it causes the water to be stratified and layered. And we talk about the AMOC often. We worried about the AMOC slowing down and collapsing. Well, the SMOC, the Southern Ocean version, has slowed down as much as the AMOC has slowed down just about, but it's done it in 10 years, last 10 years, instead of the last 40, 50 years. So this is a huge problem. As Yan said, I need t-shirts. What happens in Antarctica doesn't stay in Antarctica.
Full. I mean, it's a global weather
Yeah,
map. I had once a
yeah.
study which looked at the effects of sea ice loss around Antarctica, and it spills over all the way to the Arctic. And sea ice loss, they have actually global effect. It's like knock on, like sea ice loss disturbs mid-latitude circulation, disturbs tropical circulation. This can lead to disturbation in the other hemisphere mid-latitude. So it's like clack, 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 clack. So if you have sea ice losses at both poles, like one study were analyzing the effect of both sea ice losses, and they were expecting it's additive, so it adds up both changes. But maybe I think highly likely it's synergistic. It's more than the parts. So if you lose sea ice at both poles, creates more weather weirdness. But also with sea ice, like I had once like this reason reversal, not of the AMOC, which was wrong in this press release, but what we have for sure is warm water coming now up. It's being mixed to the surface again around Antarctica, down up to 60 degree of latitude. And this reason reversal of warm water coming up, not AMOC reversal. That's not. But warm water is coming now up around Antarctica. Other study on sea ice also had a signal. The last 3 or 4 years it emerged. It's really striking to see how suddenly the surface is starting to warm around Antarctica. And also the Southern Ocean had been an ocean region that had been cooling, very weak cooling signal. But also this reversed now into a strong warming signal the last 5, 6, 7 years or something. So the whole system in the Southern Ocean is now rapidly changing, and also it's expected that the changes of the sea ice and the interconnection with the atmosphere, it's self-reinforcing. Means you get sea ice loss, you get warmer ocean, feeds back on the atmosphere, stronger low pressure system, more moist air transport, or more warm water reaching the sea ice and melting the sea ice. So it's expected that it's a self-amplification process that happens there. Also in the part, likely also like in the Arctic, but maybe it could be really the case, like you say, the Antarctic sea ice could be vanished faster than in the Arctic, but we have no idea anymore. That's
Yeah,
also
yeah.
interesting. We have no idea anymore how this system will react. It just surprises us all the time in unexpected ways. And this is also interesting that models are really trailing now after all these changes. They do not project them anymore. Also, this waves expansion of heat waves in 23, 24. Did we get a warning from the models? Like, we get a real problem with heat waves. They will expand massively. No warning, no nothing. Because the models did not project it. And this is really frightening in a way.
Yeah, I mean, the heat waves in 2023, 2024, they rocketed at global average temperatures above 1.5. And scientists with their models couldn't basically believe what was happening. And the wildfires, of course, in Canada in 2023 directly related to those heat waves. And we're getting, I call it weather weirding, weather wilding, weather
Yeah.
whiplashing. I mean, it swings from one state to another. So I don't know, Dale. I'm sure you have lots of questions. So have we lost you completely, or
Well, you were so intense in your conversation. I thought I'd just let it roll. I mean, it was going so well.
Well, we can just
So
continue, but let's have a few questions.
Stays
how
for
can I get
sure.
a word in edgewise between the two of you? I mean, really, but that's fine. So let's talk about the albedo of the Earth, which of course is hugely important. The polar ice stay clean and white instead of turning to as the blue ocean event that this is the first time I've heard that the Antarctic is threatening to. That's a huge, massive of glacial ice. Hard to think that that's going to turn to ocean, but
It's
is
doing
it?
summer,
And
doing summer.
what's happening with the albedo of the Earth in the last decade?
Where
I'm
where the
polite.
Earth, the Earth is it, metaphorically and physically, the Earth is getting to be a much darker place. Metaphorically, psychologically, look at all the dystopian fiction that's coming out and all of the chaos and craziness. A lot of it is governments responding to reduced resources, really, saying we want everything ourselves because we're going to be on a very limited Earth. How are we going to grow food if the whole climate system shifts, which is what we're doing? Like the rain happens in places where it didn't before. It's going to be a very chaotic sort of situation. So the
Well,
albedo, let's
farmers
talk
around
about
the world
clouds.
are saying that the
Yeah,
farming around the world is becoming threatened by changing conditions. Of course, we've ruined a lot of the soils with our Haber-Bosch process, extensive use of
nitrogen. Yeah,
pesticides and fertilizers instead of replenishing the earth. People are totally unaware of the circularity of the earth system and its the importance of maintaining the nutrients in the soil. So as we lose farming, we will have serious problems, and the world will probably go into a Me Too thing, a me first kind of idea. It's not. I don't care about you because I'm starving, and it's very frightening to think where we're headed, and we're already looking at very autocratic governments
yeah.
taking over. Uh,
Mhm.
and 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 really looking out national interests instead of the internationalism that we would be hoping to see right now.
hmm So I mean, the temperature jumps and the wildfires in the last few years have been incredibly severe and underpredicted and stuff. We've also seen a huge spike in CO2 in the atmosphere. The problem is the oceans are becoming more stratified. There's less vertical mixing. This is really bad in a number of ways because the Southern Ocean is the biggest carbon sink on the planet. The greenhouse gases in the air get dissolved in the seawater, and then they're brought down to the ocean floor by the thermohaline circulation system, but that's slowing down, so the sink is failing, the sink is reducing. Therefore, the amount of greenhouse gases in the atmosphere is rising much faster than just from emissions alone.
Well,
So,
aside from the climate system, there's also the animal life on the planet. The fish and the land animals are integral part of the health of the system. And we've overfished, we've scraped the ocean meadows. Ocean grasses were a major carbon sink. We've taken out the mangroves, which are so critical. And on the land, we've used it up 3/4 of the farmland for grazing and growing food for cattle. So a big part of this is how we regard the rest of life on our planet, especially the animal life on the planet.
mhm. Yeah, I mean, so Jan, what are the main reasons you think for these heat waves in the last couple of years? Is it the fewer clouds, fewer low-level clouds? So the Earth is definitely darker, right?
It's
Because fewer clouds, sea surface temperatures skyrocketing, precipitation, hydrology cycle enhanced. Aren't we in danger of going to multi-year El Niños, which, you
all is
know,
possible. All is possible and all is bad. If you get a lot of La Niñas, this means the ocean takes up a lot of heat and this produces much stronger El Niños. You don't want to have that. If
yeah.
you get more El Niños, they get likely weaker because you have a higher heat release to the atmosphere. So maybe more El Niños better than more La Niñas, and suddenly, bam, comes a very extreme
Yeah.
El Niño. So either way, it goes downhill.
Yeah,
Heat.
I mean, you talk a lot about the warming in the Indo-Pacific and
Mhm.
that, and that's the marine heat waves there are huge and they're
Yeah.
expanding. There's a much larger area of them.
I
You
mean,
talk about that a lot. So,
the problem is with marine heat wave, every region is special in a way. The set of drivers is different. And also the development often is a seasonal signal, but also they get no permanent often in many regions. And like, for example, North Pacific, you have one side, you have Kuroshio, heat transport northward. This is western boundary current east of Japan, going north, transporting heat northward, and then going in the extension to region to the east into the North Pacific. And it's a massive heat transport northward. And then you have higher level of stratification. This means the upper ocean, the mixed layer becomes thinner than normal and during summer or spring. This makes the ocean surface prone for high pressure systems which can heat up the surface very fast. And if this happens, you get feedback. One thing is warmer surface oceans start a cloud feedback. Lesser clouds. Lesser clouds lead higher energy uptake of the surface oceans, which then increase stratification. And also, they seem to hold high pressure system in place, extratropical marine heat waves. So the larger they get, the more persistent they get. This we see now in the North Pacific. It's now persistent, even heating into winter. This means this marine heat wave, it is self-sustaining in a way. It intensifies stratification. It reduces cloud cover. It reduces wind speed, surface wind speed, by holding a high pressure system in place. And then you get, during summer, intensification of heat uptake in the surface column of the ocean. And eddies mix it then sometimes below the mixed layer, though you get also in the deeper air a heat depot down to 300 meters. This is now building up in the North Pacific. And during winter, you get the winter storms. They intensify via warm water. They can tap into the warm water. You get stronger winter storms that produce a larger atmospheric rivers that come from they pull air from the tropics in a band northward. And if a second storm bumps into this atmospheric river, it intensifies further. So you get knock-on effects of intensification of low pressure systems in the North Pacific, likely more warm water being drawn to the surface, being released to the atmosphere. So likely the northern marine heat wave starts now to generate a global warming signal. Not a large one, but generates maybe in October, November, December, maybe a measurable heating effect of the northern hemisphere. But we have to see. It's new. The size and the intensity and how fast it intensified came as a surprise. And this is now a fully new system in the system where we have no idea what knock-on effects it does. It controls the circulation in the whole area because it's a huge body of much more warmer water. So it moves the jet stream northward likely. But also now in winter, how will be the jet behave in the low pressure system, which impact the jet stream? So we have really it's a new configuration.
And also, I mean,
it's a completely unpredictable system that we are just astounded to see how we can possibly understand what's going to happen next. Sounds like what you're saying is that we're in a state where it's so uncertain, and we just know it's accelerating, which is not a good fact at all.
It's chaos, like it's chaotic. It's chaos, and the rate of change. Everything's happening so much faster. I really don't like the term new normal because unless you say the new normal, the new normal is going to last for a year, and then the next year there'll be another new normal and a new normal. So there is no new normal effectively. So I have to talk. Let's talk about paleo records, okay? Like Dale, the Miocene period, 5 million years ago, back 23 million years ago, greenhouse gas levels were 400 to 600 parts per million. Arctic was 18 degrees Celsius warmer than today. So the mean annual temperature was something like 4.5 degrees warmer than today. And when the greenhouse gas levels dropped 125 parts per million, the temperature dropped 6 degrees. So when we're trying to figure out Earth sensitivity, it is far, far higher than mainstream science recognizes. James Hansen is closer to reality. So the whole thing, if anybody gets a couple key points out of this whole session, is that the Earth is capable of massively large changes over very short periods of time. And it's very sensitive, and all the parts are connected, and all the parts are changing. And probably the biggest concerning changes in the last decade are what's happened in Antarctica, which we have the least amount of data and knowledge on because it's so isolated.
We can look back in the geological record and see that there were very hot periods and very cold periods, and we live in a very volatile planet that we are unaware of. Even if we weren't changing the climate, it is Earth is much more volatile than we have ever imagined.
Yeah.
Thank you both for today.
We'll let Jan just say one closing. Jan, go ahead, just say a sentence or
Okay.
two. Like, what is your key impression?
My key message is like we enter now the nonlinear phase of global warming. And this means we observe an intensification of the coupling between the systems, which forces other systems into stronger states. So if the subsystems, the variability of the subsystems intensifies, you get stronger knock-on effects and hitting into systems which lost their resilience and are more prone to large changes. This means this abruptness of changes will now fast intensify, and the next temperature jump will us bring into highly critical waters, I think. Very
So, in
dangerous.
other words, we all need to buckle our seatbelts
Yeah. This seems like to
on this planet.
this is
On
just
that wonderfully cheerful note, thank you so much, and we hope to see you again.
thank you, love. It was fun.
Yes, thank you. I think we could go on all day.